Okay, then one more thing. See, now here what I did, in both the direction I have provided 16 and 16. But now when you count, if I leave this 16 and this 16 between, you will get only 14 in other direction. Okay, so it becomes 32 plus 28. It means 60. So what I have to do is other direction I have to increase one. Let's say I take it 7. So now in one direction it will be counted as 17 and another direction it will be counted as 60. So total you get 62. Okay, and the diameter we consider as, let's say 32. This is not the exact thing we are going to do. So instead of changing the diameter, let us assume 32. We will be less than 3.5% what we have calculated. Okay, fine. Now why 3.5% is there here? Just a randomly I have taken, but this is the reasonable value. When you design a building, sometimes you will get the range between 2.5 to 3.5. Okay, so that is considered as a reasonable value. That's a considered. Okay. So our section is done. Now we can draw it.
So you need to check the confinement
Which one?
the confinement values.
Confinement I have kept as F415. Okay, the river, confinement river you are talking about.
Not the material property, but the number of confinements.
This one, diameter, then spacing, all those things, right? So confinement will not affect our sociable analysis result. So you can ignore this. Yeah, it will be little bit, but here if you change this also, later on after analysis I will show you the result. Here it doesn't, I don't know why this conformity meter is not showing any significant difference. We will find out one using the lateral reinforcement and another one by deployment. You can see what is the difference. Then we will see. Actually it should change, because if you are changing the confinement, spacing and all those things, that quality will change. So it should be reflected in the result. We will discuss this. Okay, so this is our column. Then we have to display the bottom side. Then at the top we have to also consider the degrees of freedom. Let's say we are going to apply the loading y direction. So we have to constrain y, then rotation u, then constrain x. Okay. Then load level, let's say we will apply one lateral load. Both direction, because in nodal analysis we are only considering in one direction. So if you do not consider in nodal analysis, you will see the result for other direction. That I don't want. what was the actual root in the last class? 3840. That was 20% of this one cross section multiplied by the population. So our height is 12 meter. So if we multiply this 12 meter with 4%, the critical weight ratio in the pool. Yeah.
4.8.
So let's calculate 200 interstory, but we have taken total height. Total will be total of this piece. It means this column should not be displaced more than 48 to be on the safer side, but that 48 again you have to multiply by R, response reduction factor. So if you multiply 48 by 5, let's say, so it will be 240 mm. So we will apply double that. Just to make it means beyond the collapse range also. That means 240 mm whatever you got, that is the displacement range where the column will show the collapse with you. Okay. So to show the complete beyond the collapse also, means it will go to the softening range after the peak point. Okay. So you can give higher displacement also. So let us say I'll push this column up to 500 mm displacement and see what happens. Sorry? This is not called distance, this is constraint. Okay, constraint is the direction where you are applying the load. Okay, this is because you want to record the reactions. Okay, so if this is free, that reaction will be not recorded. So this is done, then what else we can do? This. Let's make a gravity load case. Non-linear static. Mass force. Pushover load case. In this, when you are doing the pushover, it should be at the end of the gravity analysis. Okay. That means we are assuming that before earthquake, the building is already subjected to gravity load. So whatever the response under the gravity load, earthquake response will be after that. Okay. So whenever you should doing the pushover analysis, you should click on this option and this gravity should be checked. Okay. So these things will come back later. First we need to create this dynasty. That's what I am saying. In case of column, this is just a single member, so you have to do it indirectly. But in case of building, there is already an established method in etab, so that you can follow. That will show when you go to the building. I'll come back. First, let me create this dynasty. So this is like a linear load we are going to apply. So load will be increasing linearly, like for example 1 kilonewton, 2 kilonewton like that. But we are going to apply the displacement, not the load. Okay. So it will be like 1 mm, 2 mm, 3 mm like that. So it will be increasing linearly until it reaches the final value. Okay. So from 0, 0 to 1, 1. So it will start from 0 and reach the maximum. This one means this one will be multiplied by that displacement what we have applied 500. Okay, this is just a shape. It will increase linearly. So this is the pushover load case. Here I have selected the dynasty, then non-linear direct integration. So when you are going to apply the pushover for building again, we are not going by in case of building, it will not be dynasty again. Okay. So we will discuss this when we come to building. Now since for a single member there is no pushover method established in the software, so I am going by indirect approach. Then you have to first check this one, continue from the state at the end of non-linear case gravity. So you will start after the gravity load case. Then here you have to first click on this button when you are starting first time. Then these things will appear. Okay. Here you select this load pattern. Then this lateral node we have already created. Okay. Then this is the dynasty just now I have created. And this is scale factor, so we are not going to change anything here. And now this and this I told in the previous class, multiplication of this should be equal to the displacement maximum. Okay, we have 500. So if you let's say I want 1000 steps. Okay, when you save the file, there will be 1000 points. So to reach the 500. And then in 1000 points, what will be the steps? 0.5, right?
500.
It means in each step 0.5 displacement will be applied. So this will be approximately 0.4. So this is Rayleigh damping. You have already studied, right? Theory of vibration. Then here I change it to this option. It is better compared to other two options. If you want to avoid the convergence problem, you can use this scheme. Okay, now we'll first find out the period of the structure for mobile relations. Sorry? Mass source. Okay. Right. is not reducing in light load, assuming that axial load is permanent. Okay. Okay, so the first one period is 1.4 seconds, then second one period is 0.05. Yeah, that constant I have applied just to record the reaction, but in actual structure that constant is not there. Okay, that's it. So it is 1.4 and 0.05. Yes. Sorry. So this is 1.4 and this is 0.05. Okay, so now we can let's now analyze for the lateral load. Oh, sorry, we did not apply the hinges. Okay, that was here. So only in the bottom column we can apply. You can apply to all the columns, means all the floors also. But here I am assuming that this is just a single column. Okay. First we will go by fiber hinges, then we will go by PMM interaction. Fiber key and 3, then the properties, fiber definition options, the differ from the frame section. Whatever properties we have assigned in the frame sections, so software will be checking those properties and automatically calculate the hinge parameters. But this hinge length we have discussed in the last class. When you do not have any, let's say, reference, then you can go half of the section, that is the hinge length. Okay. Now our section depth is 1200 mm. So half will be 600. Okay. So this will be your hinge length. And you have to uncheck this. We are providing the absolute length 600 mm. Now you will go to assembly hinge. Select this, then distance from the eye thickness. Here how much should be?
300.
300.
Half of the
At the
hinge.
center of the plastic hinge. And it should be from the bottom end. So
Bottom.
you have to check distance from eye end. Okay. Then okay. I think I have selected the other option. Distance from distance from it is 0.3. I have written 300
mm.
Okay. So now we can analyze the conversion. Second hinge.
Yeah, property.
Property of this hinge.
Is the how you sign?
Okay. You first select the member, then go to assign frame and hinge. Okay. Here you select which hinge,
Then that part. This is for
then distance from item, then here at what point you want to assign that.
this is clear. This is done in the last one. The column to
I think you are talking about this.
yes.
Go to add new property, then select this user defined, then OK. Here any name you can give, then here select this fiber TM20, and then default from text section, and here you are assigning your hinge length and uncheck this related length. Clear? Yes.
Steps to show steps again for in the side.
Steps before.
In the side. Steps for
Okay. Steps to assembly request from the video. Okay. So first you see when you apply the fiber hinge, by default software do not apply. You have to first create the fiber hinge. So for creating the hinges, we go to define, then section properties and this option. Okay. Then add new property, user defined, then okay. And here any table. Let's say I want to create second hinge. Column hinge 2, and since this hinge is for column, so you have axial force, then movement in both direction. Okay, that's why this one fiber TM20. If you want to create any other hinge, for example, if you are talking about the bracings, you will have only axial hinge. Okay, so that time you can choose for this one, or sometimes you want shear hinge. You can appropriately choose what kind of hinge you want to create. Okay. Then you uncheck this and see here. This option means the properties in the section you have already defined. Okay, based on those, software will be checking the hinge parameters. You can take it automatically. You don't have to do anything. Then hinge length you have to provide. This either you can refer some code provisions or you do not have, then go over half of the section. Okay. Then once you have done that, okay. So this hinge is created now. Now once you have done this, then let's say I want to apply this hinge to this second story column. So select this, then go to assign, frame, then hinge, and here you have to select which hinge. Okay, then remaining thing, what you have done for first hinge. Fine. clear, right? So now let us check the result after analysis. First we'll see the deformed shape. So if you want to see deformed shape, you go to this option. Then select pushover, and time step will start from the last step. Let's say give some higher value. Okay. Then I go LSC. You understand IOLS CP, right? Is it discussed in class?
Code AC.
Immediate occupancy, life safety, collapse prevention.
Collapse prevention.
So this red color shows. See, here you have one even near the bottom of the screen. This green color shows your member is still in the IO range. Okay. Then this sky color or something like that. This shows it is exceeded the IO range and in the LS life safety range. Okay. And red color shows it exceeded the collapse prevention range. Means the member has been collapsed. Okay. And if you want to see the step by step, then you can change the step here. Now here you see 1000 step. Now I am in the 1000 step. So I want to start from, let's say, 0 step and check at what step it is collapsed. Okay. So here you go and make 0 here. Then okay. Now you can track here. Okay. I want to check, let's say, 1 minute. Yeah. So I want to say, let's say the second step. Sorry, first step. Okay, this is the first step, and here you see it is not yet activated. Means the member is in the elastic range. Okay. Then you will increase this. So it is failed in the second step itself. Okay. Second step, what is the displacement? One mm. So it is failing 1 mm displacement. Maybe our structure is too rigid. 1 by 1.2 meter by 1.2 meter with 3.5% of reinforcement. This seems too rigid. Okay, that's why it do not doesn't have this capacity to deflect much. Okay, maybe, and one more thing is the actual load is higher. So you change the actual load and see what happens. Let's start with 500 kilonewton and we'll increase. Are you getting what I am tracking here? Okay. Means I want to get this actual curve to show you what are the different aspects of it. Now since the structure is failing at the beginning itself, so I will not get a full curve to discuss. Okay. And there are some reasons why it is happening. One thing is the structure is too rigid, so it will not have that capacity to deflect much. Now why it happens? One thing may be because of high axial force, another thing may be because of load activity, because shear reinforcement
is very high.
is not adequate. Okay. So let's analyze the answer. Yeah, now see, since the actual load is reduced with the second step, still it crosses the IO range. Maybe in the next step it will fail.
No.
No, it hasn't
Third में लाइस.
failed.
Fourth में नहीं.
Fourth step,
Fifth,
fifth,
sixth,
sixth,
seventh.
7, 7, 8,
8,
9,
10,
10.
11, 12, 13.
Let us see where it is. So that was the effect of higher jet force because of period effect. Maybe we will go by this option. So now it is in 59. That's why I will make it 100. Not in 3.
How much increase? How much increase?
Sorry?
How much increase?
Jet force
500.
is 500.
500.
Not for 88. Still not paid. Right? Second step is it reached the LS stage.
Sir,
See, this color shows that is not yet
Sir,
color frame.
meaning of second stage is not.
Second step, not
हाँ stage.
means you
LS
start from-
LS mean मतलब LS meaning एक बार बताओ.
Okay, LS is right. Let's say this is your load displacement curve. So initially you have this linear elastic, then it reaches the non-linear phase, then somewhere peak.
Stiffness.
After that, this softening.
This sound.
Okay. So what codebook says, like SA41 for non-linear analysis, up to
This range.
certain range beyond the linear elastic phase, if your performance is within this range, then you can use the structure, means occupy the structure immediately after the earthquake. There will be no threat to the occupants. Okay, so this is considered as IO, means immediate occupancy. That means after earthquake, for example, suppose today earthquake happens, so as soon as the alarm comes, we have to vacate this as much as possible. Okay. Now after earthquake, suppose the building performance is within this range, so we will be allowed to occupy the structure immediately after the earthquake. Okay. But suppose the structure is performing this range,
This range.
not exactly this point, somewhere beyond this IO there will be another level which is called LS. Okay. So if your structure is means structure condition after earthquake is between this phase, that means you cannot occupy the structure immediately. There will be some preliminary checks whether the structure is safe or unsafe like that. Okay. After that, you can if the performance is coming out to be within this, then again you will be allowed to occupy the structure without any major like retrofitting or something. But suppose your structure is beyond LS, there will be another level somewhere CP. Okay, these all levels are in terms of displacement. Okay. So if the structure is between LS and CP after earthquake, that means there are some major damages occurred because of earthquake. Maybe some beams will fail, some columns will fail, but not the entire structure. Okay. So in that condition, you are not safe to use the structure. So either it has to be gone for major reconstruction like retrofitting, or maybe it should be demolished also. Okay. So these are the meaning of these three levels. Now these three levels are suggested in the code based on some experimentation or past observations. Okay. So here when we see the hinges within IO, that means it is safe to use. And between LS and CB means this is the thing what I said. So it will be safe to use after some preliminary checks. Maybe some minor damages occurred in the structure, not some major structural damage. Okay, this is the meaning of this LS. So now in this condition, at 500 mm displacement, the structure is still not in CP. It means it has capacity remained in the structure to go further displacement. Okay, so we will increase the displacement and see at what level it collapses.
Sir,
Sorry?
बढ़ा देना मैक्सिमम.
So we will increase the displacement.
Sir, first thing we reduce the axial load and structure performance will be increase. LS range will be increase. Second thing structure will be rigid. वो आपने क्या बोला था सर?
Second thing,
रिजिड ज़्यादा है इसलिए अपन को सेकंड स्टेज देखने को मिल जाएगा. स्ट्रक्चर कॉलम विल बी मोर रिजिड.
it means the observation when you see the result, you can make some judgment. So that was my judgment. Initially, what happened? We applied the highest load. Then at the second stage itself, it shows the collapse prevention limit has been exceeded. So now, based on your understanding, you can give some judgment. So based on my understanding was when actually load is too high.
Yes.
Okay. Suppose your structure deflected little bit.
Yes.
Now in this deflected condition, you have very high axial force.
Then
Because of the pre-delta effect, it will keep on increasing and fail. But if the axial load is less, so you can sustain even under deflected condition also. So that's why I have reduced the axial load.
yes.
But in your actual building, you will not be
Axial
able
load
to do
change.
that.
Yes.
Whatever load is coming, for that you have to design.
Yes.
Now since we are practicing, so I can do whatever I want.
Okay.
So now we will apply 1000 mm displacement and see. See, now it is failed. Okay? And what step it failed that we have tried in the term? What happened here is see here I have applied 1000 into 0.5, 500.
500.
So, number of output time steps is 1000 and output time steps size is 0.5.
0.5.
So total 500 step is coming. In 500 step, I have applied 1000 mm displacement. It means in one step, 2 mm displacement is coming now. Is clear, right? You have seen I have applied the lateral displacement 1000, right?
500.
Now the total step is 500 here. So 500 step is equal to 1000 mm. So one step will be counted as 2 mm displacement. Okay. So now at what step it is exceeding that we have to check. Let's say 400. It exceeded at 400. And 300.
फर्स्ट स्टेप के बाद ही फेल हुआ.
There is something wrong.
I have changed my load, sir. Every time it feels the same step.
Let's see. first get the result. Okay, now it's failed. Now what happened is, in previously what we have done in the low case push over. See, actually I did not observe this second option. SEC is written. Means this step is in terms of times, not in terms of displacement. So total time in the time history load case what we have created, that was 1. Okay. So this multiplication should be equal to that one, not the total displacement. Yeah. So when I was giving the earlier, one step is equal to more than one. That's why it was failing in 1 second step. Okay. Now you can check. We'll start from 0. And here you can observe the steps. Okay. So now this is 0. If I click on this, now it is the first step, and here you see a little bit deformation. Okay. Then second, third, fourth, like that. If you go, you have to cross 1000 steps. And let's see at what steps each creates. See how it is deforming. It starts deformation from top, then slowly goes down, reaches the bottom. Here we have crossed 89 steps, but so far it is not activated. So it means the structure is in the elastical state. So we increase here, let's say 100 step. Now you see at 100 step it has exceeded. If you go to 100 means here I cannot change. Here it maximum 1 is possible. So I have to go by other option only. Instead of that one, we will go to the load displacement curve.
0.0 right, provide 0.0.
Sorry,
0.0.
0. Yeah. Let's see whether it works or not. So 100 means 0.1. 0.1. Yeah. So we can go by this option. Then if I go to 0.2. 200, no heat. 0.3. So at 300 step you can see it is in LS. Means before that I have to also check the IO. So maybe 0.25 I can check. So here you see, if I check 0.25 means at 250 step it is in IO. Means before that only IO is activated. So let's check at what step. So you can see up to 206 step the structure was in linear elastic stage. Okay. Then not linear elastic actually means usable stage. Up to 206 step it was in usable condition. Then at this step it exceeded that usable condition. Now from this step to up to, so if you look at the curve, so at this step the structure exceeded this limit, means now it is in this stage. Okay. So now if you want to, means after earthquake we will be analyzing the structure and check at what stage of this level the structural condition is. So since the structure is already exceeded this limit, now the structure cannot be used until further notice. Means you will first verify whether the structure is correct or not, whether it is safe for use or not. After that only you will come to know. Now we will analyze again and check at what stage it is exceeding. Now at this stage if you want to check the displacement, okay, it is 206, means total I have applied I think 1000 mm. So 1000 means 200 mm, 206 mm. So this is 206 mm displacement. Up to this 206 mm displacement, your structure is in IO level. Okay. Then from this to this, we will see after what displacement analysis is there. So now this is 284. So up to 284, that is IO to LS. Okay. Then at 285, this is 206 to 285. So this is 285 level. So at 285 level displacement, the structure is exceeding the LS level. Okay. Now it is between LS and CP, and check what is the CP displacement. So this is 516. understand the meaning of these three things. According to our IS 1893, the objective is when MC level earthquake occurs, the structure should not go beyond this displacement. Okay, means our design objective is we should design the building in such a way that when a MC level earthquake happens, the structure should survive this displacement, should not exceed this CP level displacement. Okay, that is objective, but you do not design building explicitly considering this displacement. Now this displacement can be different for different structure. For this structure, based on this analysis, I can say that for this structure, this displacement is the CP level. Okay, this is the capacity estimate actually. Whatever the column we have taken, whatever reinforcement we have provided, whatever load is acting, based on all those things, this displacement is coming to be the CP of this structure. Similarly, when you design a building, based on those material section and loading properties, that structure will have a particular displacement, which will be the CP of that building. Okay. Now that CP level of building should be higher than whatever is suggested in the code. Okay. This is what the purpose of this nonlinear analysis. Now, for example, if you go to ASC 7 code, which is the seismic design code of US, and ASC 41 also, there is a method, displacement modification method. Okay, that is given to calculate this displacement delta target. Okay, now this delta target can be calculated for MC, it can be calculated for DP, whatever you are interested in. Now say I want to use that method to calculate the target displacement corresponding to MC, and using that, for example, let's say I got 250 mm. What it means, at 250 mm displacement, your structure collapse is defined according to your design code. Okay. Now after analysis, whatever displacement you get corresponding to this CP or corresponding to any level. Okay, this is target. Now this target is falling, let's say this is 250, it is falling between 206 and 285. Okay, for example, this is the structure, and based on this calculation you got to become target displacement. Now this target is fitting in this capacity curve and checking what stage of performance your structure is. Okay, so this 250 is falling between this and this, so I can say my structure is in I over LS level. Okay, so based on this analysis, I can say this structure when subjected to this earthquake in real, the structure will undergo certain minor damages, but it will sustain the major damage. There will be no major damage in the structure when this level of earthquake actually happens. Is it clear? So this is what you do from the pushover analysis. You analyze the structure, find out the capacity curve, then determine this IOS and CP levels, compare these things with the target displacement, and check where this target displacement is actually coming, and accordingly you can judge what is the performance stage of your structure. Okay, full thing clear? So this will be defined when you first stage process this level. This will be defined when first stage process this level. So whenever any one of the inch crosses this level, that will be defined accordingly. It means suppose one member failed, this building in earthquake one of the member failed. So what will you do? Structure is now not safe. You will get out of the building. Right? You will not wait for next beam to be failed, right? Whenever you see some indication that this beam is going to fail, so you will immediately vacate the room. Yeah, failure of the beam doesn't define the failure of structure. So that's why three levels. IO doesn't define the failure of structure. IO means safety. Okay. When fast beam fails, means first beam reaches the IO, means it is hitting you now. It is going to damage. Okay. So you just better to know. So this is IO of first beam. Then this is LS of first beam or anything. Beam or anything. This is CP of first. Okay. So whenever you get indication, immediately you have to take a decision. You will not wait for the next number to get another indication. Okay. Now we'll see the capacity curve. And if you see the hinge performance here, you can check. One minute. Here you can do hinge results. Then the time you can check. Now our CP level was at what was the displacement corresponding to CP? 500 something?
506.
506.
6,000.
Let's say the time in second it will be 0.5
16.
Okay, since this is fiber hinge, here you cannot check like backward curve. This is the stress strain curve of each fiber. Okay, now here it is showing the fiber 63. So you have to go to section to check what is actually fiber 63. Here you can check. If you see here some red dot indication is coming, that means this is the fiber 63. Okay, so from this you can understand whether it is concrete or steel. I can zoom it by looking at, maybe it is concrete or steel. So you can change the fiber here. Let's say this is one more fiber. Now it is steel. From the capacity curve you can understand. Capacity means stress strain curve. So this stress strain curve is actually for steel, right? Okay. So at this level of displacement, this fiber, here you see, this is one of the steel bar actually. So this bar is at this point. Can you see my cursor? So this was the yield point. It has exceeded that yield point. Now it is in the strain hardening range. Means this fiber is not yet baked completely. Okay. So similarly, if you go to another fiber, another part, so it is even lesser displacement compared to the previous one. Maybe I can go to the next 55, 56. So these are all steel bar actually. 57, 53. This is concrete. This is also concrete. Here you see. This concrete fiber means this concrete fiber is actually the cover concrete part. From the red indication you can understand, right? Okay. So this cover part, see, this is the stress strain curve of concrete. This is the peak point. Now at this stage, the performance level is here. So this means cover concrete is completely failed. Are you getting what I am trying to say? So based on the stress strain curve, you can understand whether it is failed or not. So the dot, what you can see here is at this current time step. Okay, whatever displacement I have applied 500 something, at this displacement the stage of cover concrete is here. Okay, it means this part is failed, concrete is failed. Similarly, if you go to next one, this is also cover concrete. Now this cover concrete is in the tension. Okay, but the previous one was in, this is in compression. Then this is also concrete. This is again in tension. This is in tension. This is steel. Okay, actually I was looking for a steel bar which exceeded this limit completely, but I am not getting. So this is the way you can just you identify all the things, all the fibers and check what is the performance of each fiber, which fiber fails, which fiber not yet failed. So like this you will make your judgment whenever you want to write something in your paper. Okay, or in case of rear design also. Suppose you want to check one column. Okay. After earthquake, what happens to the column? Which rebar is expected to fail? Which rebar is expected to survive? So based on this analysis, you can see all those things. So this is one thing. Now we can go to the capacity curve. We have applied in y direction, so I have to change it to y. Then I need another displacement also. So this will be joint displacement. Story 4 and joint level 1. This will make a displacement. This one will make this force. it is something actually time is we are applying. I want to apply in the single direction. Maybe because of the time is the definition, it is applying the same displacement in both the directions. Okay, so I have to do something for that. It should not be like that. Check if there is any other option to apply this. Maybe I can go by the straightforward pushover load case definition. See, so I'll explain this pushover, whatever actually we are going to apply in case of building. Okay? So in case of building, what you do, you go to non-linear static load case, then select mass source, and as it is here, you will select this gravity load case, and here you will select either you can go for load pattern, whatever we have discussed over, that was using load pattern. Okay? But it is easy, and mostly the option selected here is mode shape. Means you go according to your mode shape. Okay? Then which mode? Based on modal analysis, you will identify which is the first mode for your direction. Accordingly, you choose it. Now I'll check this from the modal analysis and we come back here once again. In scale vector you can leave. Then model you can choose here, and behavior you can choose it locally. And here you decide whether you go for displacement control or quasi-static, something like that. Okay? I want to go for displacement control now. Okay? And maximum, as we have seen, let's try with 500. Let's say 600. Okay, then how many steps you want? I want minimum 100 steps to be safe and maximum 1000 steps. So let's say maximum 500 steps. For pushover analysis using the direct method, you do not have to consider the curve joints. Okay, so you can remove this one because this is not the actual condition. We'll check the mode shape first. So we are applying the load in y direction, and first mode it seems y, right? Okay. So we have to select first mode. And if you want, you can change this to pushover in y. And this is already selected first mode. Now let us analyze what this load case is. go for little less space. how pushover curves will stand. Okay. Now the capacities seems to be very high. You do not expect the structure to be this amount of capacity. Now since there is no load acting, only 500 kN actual load is acting, and there is no other load. So and section size is high, maybe because of some reason I don't know. So again, when we come to building, actual building, that time we will discuss all these things once again. So now this is the way you conduct the pushover analysis. The same approach what I have just shown now. Okay, in case of building, you will follow same thing. And
Non-linear elastic. Non-linear elastic.
yeah, non-linear static. Okay, and this curve is called pushover curve. In X you have displacement, in Y you have this one force. Okay, now again if you want to check the hinges, you can go to this option once again, then select the pushover, and here you will the time step. Now see, I have applied, means I just assume this is a building, so in each story I have applied hinges, and if you observe, the hinge at the top story also experience non-linear behavior. So that's why actually I told, since this is very rigid, so the entire structure will behave uniformly. Whatever the behavior at the bottom, same behavior will be at the top. Okay, almost. That's why the top hinge also experience this significant non-linearity. But in actual building, you do not expect upper stories to experience this kind of non-linearity.
That hinges will only form if there is joint at that point.
Shifted. Sorry.
This is a single column.
Single column, but I have provided hinges throughout. Okay.
Is
So
there any
assumption is single column means the bottom will have maximum movement demand. Okay. But upper storage will also have some movement, right? Maybe that movement capacity is lesser than the demand.
We are assuming that.
We are assuming that upper storage is also experiencing non-linearity because we do not know what will be the demand. Okay. So if demand is more than capacity, definitely it will be non-linear behavior. Okay. Now you can practice. You just take one simple model, assign hinges, and carry out this pushover analysis. So just practice. In the next class, we will take one building structure and conduct the pushover analysis and discuss all the performance assessment. Whatever you have to do in real. Okay, those things we will